Exercise 2253 is maybe even more challenging than the previous multi-step synthesis exercise. These are truly exercises that test your perceptiveness and how much you've mastered these exercises. They're very high-level thinking exercises. And so they tie your hands in this exercise just like they do in the previous one. Any carbon that you use to make this crazy-looking thing has to come from drinking alcohol, ethanol, which is a really simple molecule, 2 carbons with an OH on it. So somehow we have to put that together to create all of this. Perhaps the wildest thing is that if you've learned all the organic chemistry that up until this point, is that is something that is possible. It's wild to think of. Now in the analysis for this, I'm going to do this using retrosynthesis. So first we're going to come up with a plan using retrosynthesis, and then we'll write the forward reactions using the actual recipes that create the transformations. Okay, well, when you see this molecule, you would see a lot of different functional groups. And these functional groups have different relationships to each other. The two on the left are 1,3 to each other. And on the ends, whichever ones you choose, they're 1,5 to each other. Now what that should tell you is that we're going to do 2 things. First, the 1,5 relationship tells you that we're going to use the Stork Enamine synthesis. And the 1,3 relationship means that we'll either use the aldol addition or the Claisen condensation. Now remember, there are a couple differences between these in terms of the oxidation state of the product, whether you have 1 carbonyl or 2. But another difference is just you use aldehydes and ketones in the aldol addition, and you use esters in the Claisen. Now notice we have an ester here. You could probably do this either way, but because of that ester, I'm going to focus on the Claisen condensation. So the 1,5 and the 1,3 relationship between the 2 functional groups on the molecule, or the 3 functional groups on the molecule, that tells us Stork enamine synthesis and Claisen condensation. And Claisen especially because we have an ester. Okay, so let's think backwards. Let's think about this Stork enamine synthesis first. So let's think about just these 2 functional groups. We'll come back to this one later. Now when we just look at these 2 functional groups, remember the Stork enamine synthesis happens when we take the alpha carbon of one molecule, so the carbon that's alpha to this functional group, and we react it with the beta carbon, so here's the alpha and the beta carbon of a second functional group. So we're going to break this bond here. I'm going to draw those 2 pieces separately. Now I'm going to draw this retrosynthetic arrow. We haven't done a lot of practice with this, but just in case you see this in your future academic career, this arrow means I can make this from these 2 things that I'm about to draw. So really I could do that reaction there. The part on the left, I'm going to copy. It's that left part. The part on the right, I'll copy down. So we have this alpha carbon here and an alpha and a beta carbon on the other molecule. Okay, well, what we know is we need this alpha-beta molecule, the molecule whose beta carbon was attacked, we need that to be unsaturated. In other words, we need that to look like this, to be alpha-beta unsaturated. That's what makes the beta carbon an electrophile that this alpha carbon nucleophile can attack. So how can we make this? Well, there are a couple ways you can make this. You could use the alpha bromination and then do an elimination reaction with pyridine, like we saw in the last video. Just for the sake of variation, you could make that also by doing an aldol condensation. You might remember that you can if you have these alpha-beta unsaturated aldehydes, you can break them, and the two pieces that you have replace the double bond on the one that doesn't have the carbonyl with a carbonyl, and those two pieces are the pieces you could use in an aldol condensation to create this. Okay, now if we see this other molecule, you'll notice that this alpha carbon is actually alpha to two different carbonyls. So actually, we don't need to do the Stork enamine synthesis. This is already going to be a weak nucleophile. We could just do a regular Michael reaction. The question is, though, how can we make this? And you see that on the alpha position, we've added the alpha carbon of an ester. In other words, we have a beta keto ester. On the beta carbon, we have a ketone of an ester. A beta keto ester is the sort of key group that would remind you to do a Claisen condensation. And so here's that Claisen condensation we talked about. We have these 1,3 functional groups. We can make those with a Claisen condensation. So, Claisen condensation. Okay, so how would you make that from a Claisen condensation? Well, you take this alpha carbon, that was the nucleophile of this ester, so we can redraw that. And what that attacked was the carbonyl of another ester. And the ethoxy group of this ester ended up functioning as a leaving group, so that this alpha carbon replaced that to give you this bond. So those are the pieces we would need from a Claisen condensation. Now, remember, all of this has to be made out of ethanol, drinking alcohol. And so how could we make these from ethanol? Well, we could make these from ethanol. We would have to make a carboxylic acid first, acetic acid, that's vinegar, and we can make that from ethanol. And for here, these aldehydes, we could make these aldehydes from ethanol. Okay, so notice we've done retrosynthesis. We started with our product and we worked backwards at every step. I drew these special retrosynthesis arrows that really tell you I can make this from this thing, or these groups. So now that we have this retrosynthesis, let's reverse these arrows and think about how we can make these transformations happen. So first, working with ethanol. Going in the actual direction, how can we go from ethanol to acetic acid? Well, we have one bond to a primary alcohol. We want to turn a primary alcohol into a carboxylic acid. We could use a strong oxidizing agent, like sodium dichromate, Na2Cr2O7, and water and sulfuric acid. Okay, how can we turn a carboxylic acid into ethyl ethanoate? You'll notice that's what both of these are. Ethyl ethanoate, well, we're just taking this leaving group and we're taking that leaving group and replacing it with a nucleophile. This is a nucleophilic acyl substitution. So we can just take that group and have it as an alcohol. An alcohol and a carboxylic acid give you an ester. Now you would want to catalyze that with water, and if you can remove, or catalyze that with acid, and if you can remove water, you would shift the equilibrium forward using Le Chatelier's principle, so you'd get higher yields doing that. So that's just a nucleophilic acyl substitution. Once we have those two esters, we can do the Claisen condensation to get this molecule on the left. And the Claisen condensation you get when you treat the ester first with a base that matches the alkoxy group of the ester, so that if a competing nucleophilic acyl substitution happens, it doesn't change your original molecule. That base steals the alpha hydrogen from this carbon, turns that into a nucleophile. You do the nucleophilic acyl substitution, and then you just use cold aqueous acid as your second step. There. So that gives you this molecule. Now, working backwards, on this other side, how do you turn ethanol into ethanal, or acetaldehyde if you prefer? That's the common name for ethanol. Well, we want to turn a primary alcohol into an aldehyde, so we want to oxidize it, but not using a strong oxidizing agent because that would turn it into a carboxylic acid. So instead we want to use a weak oxidizing agent. That would be like PCC in dichloromethane solvent. That would give us those ethanal molecules. And then if you want to do the aldol condensation, you would just need to add sodium hydroxide, water, that would do the aldol addition, and then heat to do the condensation, the elimination, to get the alpha-beta unsaturation. And once you have those two molecules, you can put them together. We don't actually even need to do the Stork enamine synthesis because this molecule, the alpha carbon there, is alpha to two different carbonyls. So this is alpha to two different carbonyls. So you can just use a base to steal that off. You can just use a base to steal that alpha hydrogen, and the base you would want to use would want to match the ethoxy group of the ester so that if it did a nucleophilic acyl substitution, it wouldn't change the ester. So sodium ethoxide would be a good base to steal that alpha hydrogen off. That would turn into a nucleophile that could attack this electrophilic beta carbon of the alpha-beta unsaturated aldehyde. Man, if you're understanding what I'm saying, you should really pat yourself on the back because I'm speaking a different language right now, the language of organic chemistry. You should really be proud of yourself. The second step would be adding this alpha-beta unsaturated aldehyde, and then the third step of a Michael addition is to have some acid, aqueous acid there, and that will give you your product. So this sort of work of art, this mosaic of carefully crafted tesserae can come together to create this wild and crazy molecule just from drinking alcohol, ethanol. And of course, this specific synthesis doesn't happen in living things, but you could see how using just a few reactions, living things can use these same reactions, these same principles to create wildly diverse molecules that allow the living things to adapt to the constantly changing geologic surface of Earth. Create whole legions of creatures to fill every possible ecological niche. And it doesn't take a lot of reactions to get a huge wealth in possible molecules. Okay, let's follow the same, let's practice that again with this other molecule. So again, we're going to try to make this just from drinking alcohol, ethanol. It will be a test of our wits and our ingenuity. And I'm going to approach this in a similar way, first thinking through it in terms of retrosynthesis, and then changing the retrosynthetic arrows to normal reaction arrows and thinking of what recipes we would need to make the transformations happen. So when you look at this, you would see two functional groups. So it's a difunctionalized compound, and they are 1, 2, 3, 4, 5 carbons away from each other. So that should suggest that we're going to use the Stork enamine synthesis. Whatever else we do, we can use the Stork enamine synthesis. Now, whenever you do the Stork enamine synthesis, you have to have carbonyls, because it's a reaction that depends on the nucleophilicity of the alpha carbon, the carbon next to the carbonyl carbon. So let's redraw this molecule as our first retrosynthetic step. So we could make this molecule from a version of itself that has carbonyls instead of OHs. So that's that same molecule, just with the carbonyls instead of the alcohols. Okay. Well, now that we have the carbonyls, it'll be a little easier to visualize the Stork enamine synthesis when you do the Stork Enamine synthesis, you need sort of two pieces. One piece that you need is a molecule whose alpha carbon can act as a nucleophile. So on the left here, we sort of have acetaldehyde, or ethanal. The alpha carbon on that can act as a nucleophile and attack the beta carbon of this other molecule here. Now, in order for that to happen, the alpha carbon in orange, this alpha carbon of ethanol, is going to act as a nucleophile, and the beta carbon has to be an electrophile. In order to make that an electrophile, you need an alpha-beta unsaturation, so we'll have to have a pi bond there. Okay, so we'll need those two molecules. Now, technically, if we do the Stork enamine synthesis, this will have to be an enamine, because this would act as too strong of a nucleophile. It would attack the carbonyl carbon rather than the beta carbon. So if we have the enamine, if we turn it into an enamine first, then that's a weak nucleophile that will attack the beta carbon electrophile instead of the carbonyl. We can make that enamine from ethanal, and we can make ethanal, as we've seen, from ethanol, drinking alcohol. Okay, so that's one possibility. Now let's look at this alpha-beta unsaturated aldehyde. How can we make that? Well, we saw in the previous exercise, you can make these alpha-beta unsaturated compounds by doing aldol condensations. You can sort of break the bond between the alpha and beta carbons. The compound that already has a carbonyl, just redraw that exactly as it is. So we have ethanal there, and this other one, the one that doesn't have the carbonyl, redraw it, but where the double bond was, put a carbonyl in. So you can do an aldol condensation with those, but those are ethanal, and we can make ethanal, as we know, from ethanol, drinking alcohol. And so this is our sort of retrosynthetic plan. Thinking backwards from the final product, this is how we can make this crazy hunk of carbon. Okay, now that we have this sort of retrosynthetic plan, let's reverse these arrows and think about the specific recipes we would need to make these transformations happen. We can turn ethanol into ethanal. We can turn a primary alcohol, this carbon that has the OH on it is just bonded to one other carbon, so it's a primary alcohol. We can turn that into an aldehyde by using a weak oxidizing agent like PCC in dichloromethane solvent, so pyridinium chlorochromate. And we want to use a weak oxidizing agent here because a strong oxidizing agent, like sodium dichromate, would take this to the carboxylic acid. We don't want that. We can turn that aldehyde into an enamine by adding a secondary amine. So 2 R groups, nitrogen, 1 hydrogen. The bond to the hydrogen is what gets replaced by the bond to what was the carbonyl carbon. You would want to have an acid catalyst and remove water to increase your yield using Le Chatelier's principle. Okay, so much for the enamine. Now let's think about the alpha-beta unsaturated aldehyde. We could turn ethanol into ethanal by doing the same reaction we did before, turning this primary alcohol into an aldehyde. Notice the number of bonds to oxygen increase, so we wanted to use an oxidizing agent, but a weak one, PCC, pyridinium chlorochromate, in dichloromethane solvent, and that will oxidize this to an aldehyde. You can't use a strong oxidizing agent like sodium dichromate in water and sulfuric acid, because that would turn this into a carboxylic acid. Okay, once you have those ethanal molecules, you can do an aldol condensation to create an alpha-beta unsaturated aldehyde. And here, all you would need to do that is to add sodium hydroxide and water. That does the aldol addition. That would give you the beta hydroxyaldehyde, and then heat. That does the elimination reaction to give you the alpha-beta unsaturation. Now, I realize this is all very complicated, but this is a cumulative problem. This exercise assumes that you have already learned the individual steps in the previous part of the chapter. Once you master those, making these connections is another cumulative skill that builds on top of those. Well, once we have our enamine and our alpha-beta unsaturated aldehyde, we can do the Stork enamine synthesis. The Stork enamine synthesis, which really is just taking the enamine, treating it first with this alpha-beta unsaturated aldehyde, and second with hydronium or aqueous acid to remove the enamine and to help the ketoenol tautomerism happen. That would give you this molecule, and going back from that molecule to the molecule we wanted, we just have to do a reduction. We have 2 carbonyls, carbons that are double bonded to oxygen. Here we have 2 alcohols, carbons that are single bonded to oxygen. That's reducing the number of bonds to oxygen, so we need to use a reducing agent. We can use a strong reducing agent like lithium aluminum hydride, and then just follow that up with a water wash to do proton transfers to stabilize any negative charges on oxygens that we form. And so we were able to form that really complicated looking molecule just from ethanol. So when you see small molecules, don't just think, oh, that's the beginning part of a class. That's the simple part of a class. Those small molecules can be turned into everything. All it takes is ingenuity. A little ingenuity and you can take the simplest things and create the whole world. Well, almost. Certainly that's what it seems like when you do the multi-step syntheses in this exercise.